Okay, so I guess you can tell I was able to move back up to the school, which is nice because we got more bandwidth. So you probably can tell a difference. I hope you can tell a difference in my video and audio quality. It should be better. Um, the light should be a little. I think there's some reflection on the board, but this is way, way better. Then I can use the copier and equipment to make sure you guys have the rest of the things you need. So I'm happy to be back at the school. And I called most of you. There's a couple people I couldn't get a hold to, but I called most of you. I think sometime last week to try to come up with a common time to meet for lab. And I think what I figured out is that because of some obligations that people have, we won't be able to go past the allotted time, and it is also be better if we met for lab on the assigned day. So what I want to do is this will be our last week of theory. We'll do today. We'll do Wednesday. I may do something when you get here on campus. It just depends. But this will be the last week of theory. And then what I want to do is we're going to make next week our lab week. And I want to give you something to prepare for that. There's a video document you have to do that's going to count as a lab. And since I have use of the projector now, I might be able to give you some other labs before we come up and do the oscilloscope stuff. But what I'm looking at is next Monday and next Wednesday meeting at the school to perform the labs on the oscilloscope. On Monday, I'll give you a exercise on the analog scope. We'll go through. We'll do some review with it, and then I'll give you a lab or two on that. And then the other one for the analog scope is kind of a self-directed lab where you'll go through on your own. I got a really nice tutorial. You'll go through and you'll do certain things on the digital scope. And then that'll be it. So we'll finish up this week with lecture. Now I did talk to, I think I talked to Jacob. I believe it was Jacob. We talked about possibly me recording some of the stuff that we won't get through, like the three-phase and whatever we don't get, maybe just recording that and putting it out there. That is a good idea. I think I might do that and have you guys watch it, but I won't go into a lot of detail because you won't be able to ask me questions. So this will be it. We'll do today. We'll do Wednesday as lecture, and then next week you'll be able to come up to the school and do the lab. Now, when you come up to the school to do the lab, I'll have to see what I know. We'll need masks. You have to wear masks. And we have to respect social distancing, but I think there's only one, two, three. There's 7 people listed on the roster, but I've only been getting like 5 people showing up. So I don't know. I think we got plenty of room in this lab, so I think we can spread out and make this one lab work, and we shouldn't have any issues. We'll see though. So I'll be getting back to you on specifics of that. But go ahead and write that in. Plan on next Monday and next Wednesday, meeting at Cincinnati State, room 206. And I'll have to get back to you as the school gives me information. As we get closer to the date, I'll give you information. And then we'll meet, get the lab stuff out the way, and then we'll be done. What I want to do today, though, is start a new subject. So last time we talked about transformers. We spend a lot of time talking about transformers. You know I can use a transformer to step voltage up. I can use a transformer to step voltage down. I can use a transformer as an isolation device. And then you learn that you can use a transformer for what we call impedance matching. And you do that when you want to get maximum power transfer. So we went through all of these applications for a transformer. Well, it turns out that there's one more application of a transformer that we can talk about. We can also use a transformer as a filter. So we're going to talk about how you would do that. And actually, the lecture today is based on, or is going to deal with filters, electrical filters. So that is the topic of today's lecture. So we're going to spend the day talking about filters. It may spill over into next period. I don't know. We'll have to see how it goes. But I do want to talk about filters. So let's talk about filters. Now, when I say filters, I mean electrical filters. But just in general, let's talk about any old filter. What are filters used for? What do I use a filter for? First of all, give me some examples of some filters that you're familiar with. Anybody? Give me examples.
Like a oil filter for your car?
Oil filter. Yep. Oil filter. What else?
Air filter, fuel filter.
Yep. Exactly. Air filters on the furnace, a fuel filter on a car, a coffee filter. If you drink coffee from the grinds, a coffee filter. There's filters you can put on your tap when you get tap water to filter out some of the impurities in your water. So looking at all these filters, what do filters do? What do they do? And don't tell me they filter. What does that mean, to filter?
Remove things that you don't want.
Remove things that you don't want is exactly right. So all filters do that. All filters remove things that you don't want, including electrical filters. They remove things that you don't want, and what they remove usually are frequencies that you don't want. Really, a frequency is not a thing. Like voltage and current are things, but I can have a voltage of a certain frequency. I can have a current of a certain frequency. And if I want to, I can use filters to remove those voltages and currents that I don't want. So they're kind of, as you can imagine, they're very, very useful for cleaning things up. So I want to talk about filters. And there actually is a handout that goes with this. Of course, I didn't put it up in time, so but it's just there's just a couple points on it. So I'll put this up on Blackboard, but I want to talk about wow, is it getting ready to rain out there? I hear thunder. I'm looking out the window right here, and the trees are like going crazy, and I hear thunder. Who's out there? Randall, where are you at? Are you in Kentucky? Are you there, Randall?
Yeah, I'm here. I'm in
It's coming down pretty hard.
Yeah, Kentucky. It's just started pouring just now.
Okay, and Sam, you're in Blue Ash, aren't you, Sam?
Yeah, I'm over by like Kenwood Mall. It's coming down pretty harsh over here too, Chief.
So I'm at the school. It's not raining here yet. Tressa, where are you at?
I'm at home.
Fair enough.
I mean, what neighborhood? I'm trying to see where. Huh? Well, in Clifton, it's not raining yet. So I'm just trying to remember if I think I rolled my. Oh God, I hope I rolled my windows up. Gosh.
You better run,
All right.
man. You gotta check.
Yeah, you guys mind holding on just a second? I hate to do that.
Hey man,
Well,
I'm at
hold
home.
on.
I'll just make some pizza rolls or something. I'll
Yeah,
wait.
you can talk to each other. While I'm gone, you can talk about me. I won't be able to hear you, so you can talk about me while I'm gone. I'll be back. It'll take me a couple minutes. Let me just run and make sure I let my windows up. I'll be right back.
Hey Randy, room 206, that's the same spot as it was last semester, right? That
Yeah,
in lab?
thanks, man.
Okay.
Yeah.
Okay, guys, I'm back. So thank you for doing that. I actually had my windows down, and as soon as I got out there, it started raining, started pouring down. So I was able to get my windows up, and I moved my car to a closer spot. Okay, so sorry about
So that's extra credit, right?
that. Yeah, I should give you extra credit. You saved me from sitting on some wet seats. Now, so I think it was Jacob that mentioned filters take stuff out that you don't want. So your oil filter removes dirt, your coffee filter removes grinds, air filter in your furnace removes air particles, and sometimes they have charcoal filters that can actually remove chemicals. Filters take out stuff that you don't want. The electrical stuff that you don't want are or can be voltages or currents of a particular frequency. So filters, when you think frequencies, that's an AC thing. So filters only work with AC, but DC can be thought of as a special form of AC. DC can be thought of as AC with a frequency of 0. So we can take out whatever we want with the filter. Now, why would we want to do that? Well, typically currents or voltages that appear in a circuit that are not supposed to be there, we call that noise. So we can use filters to remove noise. And this topic of filters is a really, really big topic. You can really do a whole master's thesis just on filters. So people who get into the details of this, you can spend a long, long time studying filters. So of course, we're just going to skim the surface of filters. And what we want to do is understand, first of all, how filters work, and then how would you apply them to a circuit or to a system. So let's look at that. So let me start by mentioning that there are many, 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 many different types of filters, but all filters do the same thing. They separate stuff out that you don't want. Now, the filters we're going to talk about are called RCL filters. So R for resistor, C for capacitor, L for inductors. So this is a filter designed using resistive components and reactive components, either capacitors, inductors, or a combination of the two. What we're going to do specifically for what we do in this class, and only because your book does this, we're going to concentrate on RC filters. So we're going to use the R and the C and not the L. But there's no reason why, once we go through this, that you can extend your knowledge. You can add inductors to it. You can have an RC filter. You can have an RL filter. You can have RCL filters. And all different shapes and forms, they all come with their advantages and disadvantages. So it just depends on what you want to do. The purpose of this discussion, though, is just to understand basic filters and apply the knowledge and apply that to a basic circuit or system. So let me start by saying there are 2 basic filters and 2 derived filters. So I'm going to write down the names. And then I want to talk about something called filter action, which applies specifically to the type of filters we're going to talk about, which are RC filters. So here are my 2 basic filters.
You can't see what you're writing. Can you move to the right a little bit?
Oh, okay.
Or move the camera, whatever.
Is that better? Am I going the right way or the wrong way?
You're going the right way. That's it.
Can you see it? Okay.
I see filters, and then I see L.
Okay.
Yeah,
That's
but
it. Thank you.
that's on like the very border of the screen too, though. So you'll need to go from where the L is to the right for your drawings.
Okay. How about right here?
That's good.
So you can't see this strip right here?
Correct. I cannot.
Let me move that. Can you see that aluminum strip now?
Negative.
Okay, well, I'll just start right here. Can you see this?
Affirmative.
All right, so my basic filters are low pass, and high pass. Those are my basic filters. The low pass filter and the high pass filter. Now, when you deal with filters, what they do is they use these abbreviations. So I'm going to use abbreviations just so you can get familiar with them. So for low pass, they'll call that LPF, high pass HPF. So low pass filter, high pass filter. Those are my basic filters. And then you have derived filters. So there's two derived filters. There's the band pass, and there's the band stop. Okay, so the band pass filter, which is and the band stop filter, which is okay, so my basic filters are these. My derived filters are these. And what I mean by that is these are the two basic filters. Now, if I want a BPF or BSF, I make it from these two. These are the two basic ones. I can make any kind of filter from these two right here. So those are my filters, and these are the abbreviations for those filters. Now, each filter has what we call a pass band. Let me write that down. Every filter, so we're getting into some of the vocabulary of filters now. So write this down and make a column on your paper for vocabulary words, because filters come with its own vocabulary. So the pass band. What is the pass band? Well, the pass band is the first word in the name of the filter. So the low pass filter. So the pass band will be low frequencies. A pass band are the frequencies that's allowed to pass through the filters. Any other thing is, we say, rejected by the filter. So a low pass filter, the pass band would be the low frequencies, and the high frequencies are rejected or stopped. For a high pass filter, the high frequencies can pass through the filters, the low frequencies are stopped. A band pass filter, I have a whole band of frequencies that can come, but a certain other part of the band is stopped. And a band stop filter, I have a whole band of frequencies that I don't want to go through the filter. The band stop filter has a second name. I'm going to put it down here in green. It's also called a notch filter. I'm going to spell it right here, because I don't know if you can see it over there. It's called a notch. So the band stop has a second name called a notch. So write that down on your paper somewhere. So the pass band. The pass band is the group of frequency, the frequency or group of frequencies that's allowed to pass through the filter. Now, let's talk about filter action. Now, filter action only applies to RC filters. Remember, you're going to have RC filters, you're going to have RL filters, you're going to have RCL filters. So filter action only applies to the RC filter. So let's write down filter action. And then after I do that, I'm going to talk about the two categories of filters. There's 4 types of filters, but 2 categories. So filter action. I'm going to abbreviate because I don't have a lot of space. All right. So write this down, filter action. So for filter action, and this is for RC filters only, for high frequencies, let me underline the word high frequency. If your filter is designed correctly, for high frequencies, the capacitor is going to act like a short circuit. For low frequency, the capacitor is going to act like an open circuit. Right now, because as I go through the filter types and we understand how they work, in order to really understand how they work, you got to understand this. For high frequency, the cap acts like a short circuit. For low frequency, the cap acts like an open circuit. Well, okay, well, what does that mean? Well, let's go back to the expression for capacitive reactance. Let's go back to that expression. If you look at that, you see that XC is 1 over 2 pi FC. So the 2's a constant, the pi's a constant. Once you go by a capacitor and solder it in the circuit, C is a constant. The only thing that can vary here is F. And depending on the value of F, if all the other variables here are constants, you get a certain value of X of C. Now, it says for high frequencies, the capacitor acts like a short circuit. What does that mean? Well, just look at the equation. As I make this frequency higher and higher and higher, what happens to XC? As F gets higher, if these other quantities are constants, then XC gets lower. So the higher my frequency, the more of a short circuit the capacitor becomes. The question is, how much of a short do you want it to be? And that really depends on the rest of the circuit. See, if I have, say I have 1 trillion with a T. If I have 1 trillion ohms right here, 1 trillion ohms, and I have 100 ohms over here in parallel with it, then compared to 1 trillion ohms, that 100 ohms is a short circuit. So what I mean by a short circuit depends on what else is in the circuit. But this is what I want you to remember. For high frequencies, the capacitor acts like a short circuit. For an RC filter designed correctly, you design it so that a high frequency here will give you a low enough XC that for all practical purposes it's a short. And you can see the reverse is true too. For low frequencies, the capacitor acts like an open circuit. So now what if I take this frequency, instead of increasing it, I start to decrease it? What's going to happen to XC? Well, as I start to decrease it, XC is going to increase. It's going to get higher and higher and higher. The lowest I can get is 0 hertz, but that right there is DC. We can consider DC to be a special case of AC. DC is AC with a frequency of 0. And if I put in a frequency of 0, if I put in DC, then this is going to go all the way up to infinity, which is an open circuit. So, to understand the way an RC filter works, you got to understand filter action. For high frequencies, the capacitor acts like a short circuit. We're going to use that to understand the filter. And for low frequency, the capacitor acts like an open circuit. Now, let me back up because there's 2 key words here that I want you to look at. What do we mean by high and what do we mean by low? So mathematically, you got to state that. Now, not for this class. This is something for when you get to electronics and you really get into filters. You can start defining, all right, this is what I mean by a high frequency, and this is when that capacitor should act like a short. Or this is what I mean by a low frequency, and this is when that capacitor should act like an open. So you can mathematically set those values to have the filter behave the way that you designed it to behave. But that's not what we're going to do here. We're going to take the easy route and just say, if I have I'm not going to define high. High frequency could be whatever you want in the design. But for we're going to assume we have ideal devices. So my capacitor is either a short or open for right now. So for high frequency, you remember that capacitor acts like a short. And for low frequency, please remember the capacitor acts like an open. If you got that down, that's filter action. Now here are my different types of filters. Low pass, high pass, band stop. There's two categories of filters I want to talk about. Let's talk about the two categories. Now I'm going to erase filter action, but you got to remember it. So I hope you wrote it down in your paper somewhere because I'm going to refer back to it. Okay. My two categories are categories of filters. I can have all four types under two categories. I can have either passive filters, or I can have active filters. So I can have any one of these four, but they can be passive, they can be active. So the easier one to talk about first is an active filter. So what is an active filter? Well, to talk about that, we got to talk about something that's a little advanced, but you probably heard of it. Everybody's heard of an amplifier. Everybody's heard of an amplifier, but not everybody understands what an amplifier is. What does an amplifier do? And don't say it amplifies, because if you say an amplifier, I'm going to say, okay, what do you mean by that? What does an amplifier do? What is the purpose of an amplifier? What does it do? See, some of you were going to say it amplifies, and since I said you can't say that, now you don't want to say anything because you can't use the word okay, an amplifier amplifies. So what does that mean? What does it mean to amplify something?
Wouldn't it mean it's a way of increasing a certain measurement that you desire?
Okay. So I think that was Sam. He said a way of increasing something. So that's correct. Let me tell you the wrong answer, because most people say an amplifier makes things bigger. So let's say an amplifier makes your voltage bigger or makes your current. That would be the wrong idea. That's not what an amplifier does. For amplification to take place, we're talking about one specific thing. For amplification to take place, there must be an increase, not in voltage, not in current. There must be an increase in power. There must be an increase in power. So amplifier, I can have an amplifier. The way you draw an amplifier is like this. In electronics, we usually draw inputs on the left. So this is my signal in, and this is my signal out. So on the schematic, we usually draw inputs on the left and outputs on the right because we read from left to right. And let's say this is an amplifier, and the gain, this is something called gain. The gain of the amplifier is 2. The gain is like a multiplication factor. So whatever I put in here will be multiplied by 2 times. So if I put in 10 watts, over here I'll get out 20 watts. If I put in 100 watts, over here I get out 200 watts. For true amplification to take place, there must be an increase in power. Not current, not voltage, power. Now, why am I saying that? Well, because if you give the wrong answer, like a lot of people say, all right, an amplifier is going to make the voltage bigger. Well, it might, I don't know. An amplifier is going to make the current bigger. It may be so. But think about a transformer. What if I have a step-up transformer? Let's look at a step-up transformer. If I have a step-up transformer like this, so let's say I put in 120 volts here, I get out 240 volts here. Does it amplify, did that step-up transformer amplify our signal? And the answer is no, it did not. It magnified the signal, it magnified the voltage. But remember, for a transformer, the power on the primary and the power on the secondary have to what? They got to be equal. So there was no net gain of power. There wasn't any power gain. So transformers cannot amplify. Transformers can magnify. They can increase the voltage amplitude at the expense of the current, or they can increase the current amplitude at the expense of the voltage. But the thing about it is the power going into the amplifier, to the transformer, is equal to the power coming out if I have an ideal transformer. So there's no amplification here, nor do we want that. That's not what a transformer is for. So transformers do not amplify. We can say they magnify or they step up, but there's no amplification. Now, if for some reason I put in a certain amount of power on the primary and I got out more power on the secondary, then that would be different. But then we'd be violating the conservation of energy principle. So now you hear why I say for true amplification to take place, there must be a net gain in power. There must be an increase in power. So amplifiers increase the power. Now, it doesn't create energy, it doesn't create power. What it does is it takes power from somewhere else in the system. You got to ask your teacher about that when you get to electronics. If it's me, I'll go into it. If it's somebody else, you got to ask them and maybe they'll go into it. But just know, for true amplification to take place, there must be an increase in not voltage, not current, but power. So here's my amplifier. Now, what is an active filter? Well, an active filter is just one of these regular filters. So I might have let's say a low-pass filter. Now, usually when we draw a filter, we just draw it as a box. So here's my low-pass filter. To make it an active filter, what I do is I take an amplifier and I hook it to the output of the low-pass filter. So I take my amplifier and I hook it here. And I put this inside of one box. So I got my signal in and my signal out. So an active filter is a passive filter plus an amplifier. So now you know what a passive filter is. A passive filter has no amplification. Passive filters are what we call lossy. The word, I think it's spelled like this. I don't think it's EY. Lossy, that's the actual word. And what that means is you always end up with less power than you started with. So a passive filter is just a filter built out of resistors, capacitors, and or inductors. No amplification at all. And you always get out less power than you put in. The reason is you have a resistor in the box. And remember, capacitors and inductors, as we know, they cannot dissipate power, ideally. But a resistor can. And since a resistor is the basic part of the filter circuit, there's going to be power, there's going to be energy converted to heat, so there's going to be a power loss. So we say passive filters are lossy. What an active filter does is it replaces the power that's lost, and in some cases, it actually builds up the power like we did right here. So I can use the filter, the low pass or high pass filter, to separate the frequencies. And then I can use the amplifier to build it back up to where it was or even higher than it was, which in most cases is what we want. So you should know the 4 different types of filters: low pass, high pass, band stop. You should know the 2 basic filters, the low pass, the high pass, and you should know the derived filters, the band pass, band stop. And by derived, I mean it's made of these 2. And then you should know there's 2 categories of filters. I can have passive filters and I can have active filters. All a passive filter is a filter with no amplification. An active filter is a filter with amplification, and that's that story. So anybody have any questions over that? All right, well, let's look at how does this filter work? How does it work? We're going to start with a low pass filter. Let's look at it, how it works. So I'm going to draw the most basic low pass filter you can have. So here's my basic filter circuit. And what you do is you put it in the box. So imagine this is in the box. So imagine you couldn't see inside the box, but I really want you to see inside the box. So here's my box. So what I really have then is this. I got this box. Over here is V out. And over here is V in. And you know that this is a filter. But let's say you got Superman, you got X-ray vision, and you can see inside the box. Well, if you look inside the box, that's what you see. Okay? Input, output, components. Now I'm going to erase the box here. I just want you to, I want this to be a little cleaner, but just imagine this is in the box. Now I'm going to do something that we haven't done before. I'm going to hook up 2 AC sources in series. They don't have to be in series, they just have to be together. But I'm going to hook up 2 AC sources in series. So I'm gonna hook this up right here. Okay, let me erase this. I'm gonna hook up two AC sources, but I'll make one purple and one orange or green. So this is my F high, and this is my F low. So high frequencies means that the waves are real skinny. They're together like this. And low frequencies on the old scope was going to be wider like that. So I got high frequencies and I got low frequencies. So let's hook that up to the filter. So I'm going to connect it like this. And so I got two frequencies here, right? I got high frequency and I got low frequencies, both going into this filter. Now, do you guys remember superposition? Who can tell me, just kind of in a nutshell, what is superposition? What does it say? Superposition. What's
You
the
solved the circuit for one source and wrote those numbers down, and then solved the circuit for the other source and wrote those numbers down, and laid them over top of each other to find, would that be the net?
Yes, exactly. So that's exactly right. So said another way is I can treat each source independently to see what the circuit looks like specifically for that source. That's what when Jacob was, we can turn something off, find values, turn something else on and off, and lay them over each other. That's superimposed. But said another way, I can consider each source independently, and I can add those together to get the actual thing that's going on in the circuit. So if you remember that from DC, superposition. So the high frequency circuit or source and the low frequency source, even though they're hooked to the same circuit, actually see two different things. I want to explore what they see. But you got to remember filter action. Now, filter action says for high frequencies, the capacitor acts like a what? For high frequencies, the capacitor acts like a what? When you forget that, just write the formula down like this. Proportional to one, let me make that neater. Write the formula down. XC is proportional to 1 over F. So for high frequencies, the capacitor acts like a what? A short. For low frequencies, the capacitor, if I reverse these, acts like an open. So if I use that idea plus superposition, let's see what the high frequency sees. What does this circuit look like to the high frequency? Well, to the high frequency, I would have and let me hook a load up over here. Say this is my speaker. I got a speaker here. Or a load resistor, whatever you want. Say I got a speaker or a load resistor. Can you guys see this picture right here? Is it in the camera? This one? Or not?
Yes.
Okay. Now, so here's my high frequency. Here's F high. And here's my low frequency. If I use superposition, I turn F low off by replacing it with a short, and then this is what I have. Or I turn this one off and replace that with a short, and this is what I have. So looking at superposition, I can see what each source is doing independently. Well, for high frequencies, that capacitor is going to be a what? Designed correctly, that capacitor is going to be a short circuit. So it's going to look like this. So any current or voltages that's part of that high frequency source, here's what's going to happen. Let's say it's current. That high frequency current is going to come through here. It's got to go through that resistor, so it's going to dissipate power. But at this point, it can go through that speaker, or it can take the path of zero resistance and go back to the source. Well, current takes the path of what? Least resistance. So the current from this high frequency source is going to do this. It's going to bypass the speaker because it looks like the speaker shorted out. Whereas over here for low frequencies, if I reverse this, for low frequencies, that looks like an open circuit. So over here, for the low frequencies, it looks like this. It looks like an open. So for low frequencies, the low frequencies come through here. They can't get this way because that's an open circuit. They're forced to go through the speaker, and only the low frequencies see a path through the circuit. Only the low frequencies pass through the speaker. You see how it works? So if you understand filter action, you can actually reason your way through this to see which current frequencies would pass, which current frequencies would be blocked. In this case, this is a low pass filter, so my low frequencies would pass through the filters. The high frequencies are actually blocked because they're shorted out. You see it? Now, with every filter, there's a graph. So there's a lot of graphs we got to deal with this stuff. So what I want to do is draw the graph. Now the graph has a special name. I'm going to show you two graphs. I'm going to show you the ideal graph because it helps you to understand the circuit. Then I'm going to show you the actual graph that we deal with when we do this kind of work. So let's look at this filter right here is a low pass filter. So instead of drawing that, what I would do is this. I'll just draw a box and label it low pass filter. What's in the box would be this. So I don't want to have to draw this all the time unless I'm designing. Typically, I'll replace that with just this box and label it, right? So let me give you the graph for the low pass filter. Before I do that, how would I change this to a high pass filter? How would I make it a high pass filter? What would I do? How would I change this? If you see how the low pass filter works, if you understand filter action, what would I need to do to make it a high pass filter? Something really simple I need to do. What is it?
You flip-flop the components, the resistor and the capacitor.
Yes. Everybody see that? If I reverse the components, then what happens reverses. Think about it. So let's say I do this. If I reverse, so here is I put my capacitor here and my resistor here. And let's right here, I have a low pass filter. And I got my F low. I guess that's F high. So here's F high. And here's F low. Okay, so remember, for high frequencies, the capacitor acts like a short. So over here, F high, that capacitor acts like a short. And if I have my speaker right here, or my low resistor, current can flow into the circuit. Some of the current's going to go there, but some of it's going to go through my speaker on my load. Whereas over here, at low frequencies, if I have low frequencies, the capacitance is going to be high, it's going to act like an open. So for low frequencies, this acts like an open. No current can get across the gap, so whatever I had over here, it's only going to get the high frequencies, it's not going to get the low frequencies. So I can make a LPF or I can make a HPF by just, as Jacob said, just flip-flopping the RC component. Now, let's go back to my low-pass filter, and let's see if we can, what does that look like in the graph? Ideally, let me show you what it looks like. All right, so when they talk about how a filter behaves with a curve, the verbiage they use is response. How the filter responds to low frequencies. And so the name of the graph is called a frequency response curve. You need to know that. Frequency response curve. So let me draw a frequency response I forgot how to spell response. Oh, I guess I spelled it right there. Curve. It's also called a bowl plot. So if you see that and that, they're the same thing. I like frequency response curve because it sounds smarter. People think I'm smart when I say that. Bowl plot, it's okay. I like this one better, but just know both of them. Anyway, here's what it looks like. This is the ideal response of a low-pass filter. And the way you do it is you put frequency here, and on the vertical axis, I can have a couple things. I can have voltage, I can have current, and I can have something called gain. You're going to talk about gain a lot when you get to electronics. So I'll tell you about gain in a second. But some books use a capital G to represent gain. Most books I pick up use an A. So I'm going to put an A here. So voltage and current, you know what that is. Gain is new, but it's not a big deal. So just realize on the vertical axis, or the independent variable can be V, I, or gain. Okay? So for a low-pass response, here's what it looks like. Ideally. Okay, so this frequency right here, FC, is called the critical frequency. The critical frequency. So this is the ideal response for a low-pass filter. And what you have here are some important points. This point right here is the point where V out equal V in. And I'll show you this later on. Don't worry about it. I don't know if you can read that. Let me make it nicer. So we're talking voltage. That's the point where V out equals V in. Right here, this is my pass band. That's my pass band. And over here is my stop band. And that goes all the way up to infinity. So if I had a perfect low-pass filter, this is how I would want it to behave, like this. Starting from 0 hertz up to a certain frequency, I call my critical frequency. I want all those frequencies to pass through the filter with equal amplitude. Once I get past my critical frequency, I'm at what we call, I move from my low frequencies to my high frequencies. Then I want all those frequencies to stop, not be allowed through the filters. So if I could design, if I had a perfect low-pass filter, this is how it would behave. But that's not how it really behaves. This is the ideal response. The actual response looks more like this. I guess I might have to put it a Okay? So the actual filter response curve looks more like this. Notice the top is kind of flat, but it's kind of tilted a little bit. Then over here starts to really, really drop. The slope is really, really fast. So, and let me do this real quick. So what happens is you start here. This is the point V out equals V in. That point right there. If you take 0.707 of, let's say, V out or V in this case, they're the same, so it doesn't matter. But if I take 0.707 of one of these quantities, then what I get is a quantity down here somewhere. Right? I mean, if that was 1 volt, then 0.707 times 1 would be 0.707 volts. Or if that was 10 volts, I take 0.707 of 10, then that would be 7.7 volts. Whatever I have here, if I take 0.707 of it, I get a value below that point right there. That's what we agree on. But once you take 0.707 of that, then what you can do is draw a horizontal line out like this and intersect that curve and then drop a perpendicular down. What that does is define this point that we're calling FC. And what that does for you is define your band stop. So now my pass band goes from 0 to FC, and my stop band goes from FC up to, for this case, infinity. The steepness of the curve right there. So it's kind of exaggerated there, but it's more like this. It goes over and then like that. So the steepness of the curve. Let me do something here. The steepness of that curve. So let's say I had this. So I can have the curve like that. So the steepness of that curve has a name. It's called roll-off. Roll-off. So the roll-off here, and let's say I do this. So the green line has a higher roll-off than the black line. And the orange line has the highest roll-off, the most slope is what I'm saying. Roll-off is equal to slope. So the greater the slope, the greater the roll-off. Now, this is getting a little above what we want to talk about. This is a little bit higher level, but I just want to explain something. The steepness of that curve, the roll-off, is determined by the number of RC combinations that you have. Again, I'm not going to test you on this part because this is something you'll learn when you get to electronics or other advanced courses. But remember, I had, let me go back to my filter. I need this space. Remember I had the filter like this? I had that. Well, each RC combination is called a pole. P-O-L-E, a pole. And for every pole you put in there, it causes the roll-off to get steeper and steeper and steeper. So what I'm saying is, in more advanced filters courses, you can take that low-pass filter and actually add another resistor capacitor over here in a certain way, and it'll make the roll-off go from this to this. This is a single-pole filter. If I have another RC combination, I have a double-pole filter, the roll-off might be like this. Or if I had 3 resistor capacitor combination, the roll off might be like this. So you can see the trend. The more poles I add to the filter, the higher the roll off.
Could you draw one with multiple poles so I can visualize what the schematic would look like?
I could draw it, but it would be drawn the wrong way because I don't remember what it looks like. But you can look up a 2-pole RC filter on Google faster than I can draw it.
Okay.
But it would be something like, it could, yeah, I would just look up 2-pole RC filter real quick.
Yeah, that's fine.
Yeah. The thing is, when I learned this stuff way back in excuse me, when I was in college, I haven't used it since. So I've always taught these lower level courses. So I've taken the higher level courses, and I forgot how they connect up. When you, I think that was Jacob. Guys, if you do go to Google and look this stuff up, this filter, it gets crazy because there's different types of filters. What I mean is, there's different types of low pass filters. So you can have a Butterworth filter. This one named after a Russian guy, Chebyshev filter. It gets really, really crazily in a lot of detail. So it can get complicated fast. But Jacob said, all right, well, how would I hook up? I mean, it might be, you might have another resistor here. And, I don't remember how it's drawn. But go to Google and look up 2-pole RC filter. You can get a snapshot of what that looks like. But I'm dealing with this at kind of a bird's eye level, just kind of a high view. For every pole I add, I get more. It becomes more and more like this. So in theory, I can add enough poles so that my roll off actually approaches the ideal response for a low pass filter. But what's the trade-off in doing that? Tell me what the trade-off. If I keep adding pole after pole after pole, what's the trade-off? I get a better slope or approach the ideal. But what's the trade-off here? Anybody? What's the trade-off?
Does it have to do with cost?
Okay, well, that's all. Everything has to do with cost. So yeah, it's going to be more expensive, but that's not what I was thinking about. True statement. It's going to cost more. But look at the circuit. As I keep adding stuff to it, what happens? On the basic level, what happens? The first thing that happens is it becomes a lot more complicated. Every time I add a pole, that's another 2. What if I have a 10-pole filter? You vastly increase the complexity of the circuit. So number one, yeah, the cost is going to be more expensive. Number two, it's way more complex. And number three, every time I add the C part is cool, but every time I add a resistor to the circuit, what happens? What do resistors do? Now I know you guys know this. You're just not talking to me.
You lose power, right?
Power, yeah. Resistors heat up, and if the power going into the filter is being radiated as heat, that means it ain't going to my speaker or whatever it is I'm driving with the filter. So these passive filters are lossy. Now we can get around that. We can connect the amplifier to the other end and change our passive filter to an active filter, but we ain't talking about active filters. We're talking about passive filters right now. And every time I add a pole to it, I'm going to lose more power. So remember, in engineering, really in life, not just engineering, in life, there's a trade-off for everything that you do. There's a trade-off. You can buy a bigger house, but the trade-off is you're going to pay more for it. It's going to cost you more to heat it up. You can buy a bigger car, but the trade-off is cost you more gas. You can go out and get that motorcycle that you always wanted, but the trade-off is your girlfriend, your wife, your significant other, she's going to want to buy something also. So there's a trade-off to everything, right? Well, there's a trade-off to this. So how do you know what you want? You got to just kind of balance it, pros and cons, and then make a decision. Now in here we don't have to do that because we're going to keep it simple. We're dealing with a single pole RC filter. We're going to keep it simple. So we're going to deal with just one frequency response curve. All right, well, if the low pass response is like this, what's the high pass response look like? What does that look like? Well, let's draw it. How would I want a perfect high pass filter to behave? Is the question. And you all know the answer. I want it to behave like this. I want the low frequencies not to go through. At some point, I'm calling FC, I want the high frequencies to come through and keep going through. So that would be my ideal high frequency response. And so my pass band now is right here. Here's my pass band. And my stop band is right here. If I, in a perfect world, this is what I want my circuit to act like. Again, I guess I should label it. We got frequency here. And I can have voltage, current, or gain. I'll just for now use voltage. And that's what my curve would look like. We can't have it that way. We can approach this, but we can't have this ideal response. So what does the actual curve look like? So let me draw the actual curve. This point right here, that's the point where V out equals V in. And if I take 0.707 of one of these values, I take 0.707 of V out, and I get a point down here somewhere. And if I bring a line over to intersect the curve and then drop a perpendicular down, that tells me where FC is. And so once you do that, now here's my pass band. And over here is my stop band. And the same logic applies as the above graph.
Does this graph actually start at the origin at 0, 0?
Yes. And 0,
Always?
0. Yeah, I can't think of why it wouldn't start at 0. Now, this can be shifted, as you'll see in just a second. I can shift this over, but if I have just a basic low pass or high pass filter, you're always going to start at 0. Every graph I ever seen start at 0. Now, can I shift it? Yes. And do I want to shift it? Well, sometimes. I'll explain that in just a second. But just a basic pass band, a basic low pass, basic high pass, yeah, you want to start over here at 0. Okay? Now, let me show you the responses for the other two. Well, first of all, let me show you this. Let's look at a band pass filter. Okay, so basically a band pass filter is this. You take you take two filters. You take a low pass filter and a high pass filter. The order doesn't matter, but the components that you use do matter. So I'm not going into the design of the filter. That's electronics. But just realize the order of the filter, I can switch them around. That doesn't matter. But the value you use for the component does matter. So it has to be designed correctly to do what I'm about to show you. And we're not getting into the design. This class only deals with the functionality. So what I do is I take a low pass filter and a high pass filter and I connect them up. I put them in one box. And here's my V in, here's my V out. So what I have now, if this is designed correctly, I have what's called a band. Let me just initial it. I have a band pass filter. So now what do I mean the components have to be right? Well, let me show you what I'm saying. Up here in my low pass or my high pass, what determines what is FC? What is FC? So FC is the point where XC equals R. It's the frequency at which that's true, where XC equals R. So in other words, it's the frequency at which 1 over 2 pi FC equals R. So that frequency at which that happens, we call that the critical frequency, XC. So if that's true, if you accept that, I solve this equation easily for FC, and I get FC equals 1 over 2 pi RC. And here's a formula I can use to calculate the FC here or the FC here, depending on which filter I have. But a bandpass filter, what is it? A bandpass filter is a combination of a low pass and the combination of a high pass. So what the essence is, what a bandpass filter will do is take this response and this response and add them together. And when you do that, here's what you get. You get a combination of responses. You get this response from the low pass. That don't look right. And you get this response from the high pass. But the filter action is going to cut off, one filter is going to cut off this part of the curve, and the other filter is going to cut off this part of the curve. So what you get is a response that looks like this. The combination of those two responses actually looks like this. Where this point right here is the point where V out equals V in. And if I take 0.707 of that, I get a point down here. So that's my 0.707 point. I can't write it in on the room. But look at this. If I draw my horizontal lines, now look. I got two intersections, so I have an FC1 and I have an FC2. So earlier when I said you got to design the R and the C component, you got to choose the right components, You have to design it in the way to where your FC1 and your FC2 are where you want them to be in the way of hertz or megahertz, whatever your frequencies are. So that's what I mean by design correctly. But if you design it correctly, now look at what happens. Right here you have your pass band. Now, notice I stop at the critical frequency because this works exactly like resonance. You know what happens to power. If I start here and I go down to 0.70, remember Jacob asked me that question about why is 0.707? It's always popping his head up. And I said, I don't know why. He did some research on it, but here's what I do know. That when you go to the 0.707 point, what effect does it have on power? See, we talk a lot about voltage and current, but really what matters is power, because all power is energy per unit time. And what we deal with, guys, we don't deal with voltage, we don't deal with current. In this world, we deal with energy. And so by taking 0.707, I'm looking at energy, but engineers like to talk about power. So you know what happens to power at that point is decreased to half. So my pass band is right here between FC1 and FC2. So any signal to the left of FC1 is, if it's right here, is decreased by half. Let's say it's 100 watts. Look at what happens to the power as I move further and further to the left. It's really, really decreased, or we say attenuated. Or over here on the other side of FC2, same thing. So my pass band is between those two critical frequencies, and I have a stop band right here, and I have a stop band all the rest of the way right here. My pass band is right here. So if I have an application where I want to, I have some low and some, I have a whole band of frequencies from lows to high that I want to pass through a system, I want a pass band filter, which is a combination of an LPF and HPF. Again, when you take your electronics course, you can go into the box and actually design it. But here, we're just looking at how does this function. And here you go. Well, if a bandpass filter, if the way for me to get a bandpass filter is by taking an LPF and an HPF, hooking them in series, and making sure they're designed correctly to give me the proper value of FC1 and FC2, does anybody want to take a chance on guessing how would I hook it up to give me, if this is a pass band filter, how would I connect those to give me a band stop filter? What would I do? Just guess.
Are they going to go in parallel?
Yes. Now, last time I got in trouble when I'm not going to say it, because somebody reported me and I got in trouble in the class because people take my excitement the wrong way. So, yeah, they're going to go in parallel. I mean, this logic suggests that if series gives me this, probably parallel will give me something else. But again, I'm not going in the box. We'd have to sit here probably for another, I don't know how many hours to go in the box to actually design this. And I haven't done that in, well, shoot, I graduated from college and I haven't done that in over 20 years. But whoever teaches you electronics, they could do it. Now, if I was teaching the electronics course, I would review all of that, and I'd be ready for questions like that, and I'll be able to answer all of Jacob's questions too. But I haven't touched this stuff in years, so we're doing this on a high level, and hopefully, when you take electronics, you dig into what's in the box. Definitely, if you take advanced courses, like you definitely go into the box. But as was mentioned, what I would do is this to make a. Well, I guess I have to erase this. So here's what you would do. You would take a LPF and you would take an HPF and you would connect them together like this. Here's my input. Here's my output. And you would put that in one box. So that's what's inside the box, but you couldn't see inside the box. You call this a band stop filter, but it's also called a notch filter. A notch filter. Again, you gotta design it correctly, right? So what I mean by that is you gotta put in the proper R and C combinations to put the FC1 and FC2 where you want it. But this combination of these two graphs is gonna look like this. And this is why, Jacob, when you asked, does it always start at 0? I said most of the time, yeah. Sometimes. Here's a case where it doesn't start at 0. So what you want to do is this. The response for the band stop is going to be like this. Got frequency. Now I want my low pass response to be like this. Right? And so I got this point right here. V out equals Vn. I take 0.707 of it. I drop a perpendicular down, and I get FC1. But I design it in such a way to where my high pass starts out actually over here and then continues. And this defines my FC2. So here, Jacob, when I said, I forgot how I answered your question, but here's a case where you're starting this not at 0. We combine those two filters, and I don't want this over here. I don't want them to overlap, because then I have a band pass filter. I want to design it in the way to where I have that separation. And now look at what happens. Look at this. My pass band is actually here. Here's a pass band. And here's a pass band. But just in between these two curves, this part of the frequency is taken out. So here's my band, my stop band.
Okay, so this is exactly what I was asking about.
If you have a situation, I can see in what you do, Jacob. I don't know, guys, you know the background of Jacob, and I'm not going to go into the detail of it. He can explain it to you if he wants to. But he actually does a lot of the applications of stuff that we're talking about in theory and some higher level stuff, working with cables and other things. So if there's a situation where you're dealing with AC voltages and current, and remember, DC is a special form of AC with a frequency of 0, you have a band of frequency, just a slice of it you want to take out and leave what's the rest of it, you would use a band stop filter. You see now why it's called a notch filter? Because this is like a little notch, a little like you dug out something, a notch. So that notch filter, I'm getting confused. Pass band, low pass, and high pass, you figure out which one of these you want, depending on your application, and then you're good to go. Now again, we're looking at this on, hold on a second. Okay, I had to check my time because I'll get to talking about this stuff and look up and it'll be 6 o'clock. So here's the way if you're doing some engineering with this, here's what I recommend. Again, now we on this level, we don't do any designing or any calculations that are, we're going to do some calculations, but if you're actually designing this, you have to kind of I would start with the graphs and figure out what is it you want the system to do. And then you put the graphs together, and then working from the graphs, you figure out what kind of circuit will give you the response that you want. And I'll show you an example of that in just a second. But you guys see how this kind of fits together. We're going to do some calculations. Don't worry about that. We'll get into some of the math. But you got to understand, you got to have a gut feeling for what the equations are doing. You got to have a kind of a high level understanding of the big picture for the equations to make sense. So if you see these graphs, a picture is worth 1,000 words. Well, here that is really, really true. You should know, just looking at the graph, you should know what they are, what they represent, and kind of understand how the circuit gives you, at least for the basic ones, the pass band and the low pass and high pass, how you would arrive at the shape of it from the way the circuit behaves. All right. Okay, well, I want to get into some of the math of this, but let me show you what I mean by starting from a high level and kind of working your way down with the graph to figure out what it is that you want. Let me show you an example of that. So I'm going to erase all of this. Now I'm going to ask you guys some basic questions. And we talked about this stuff before, so if you think about it, you should know the answer. All right, so here's my first question. What is bandwidth? What do I mean when we talk about bandwidth? What are we talking about? What is bandwidth? And I mean, you guys can be looking it up on your phone. Just go from what we talked about. Think back to what we talked about. We've talked about this. Don't look it up. That's easy. I don't even care if you're answering you're wrong. I don't care about right and wrong. I just care about make an answer. If you're not right, we'll arrive at the right answer together. But what is to you? When we talk about bandwidth, what does it mean to you, bandwidth? What is it?
It was like the range of frequencies that were usable for whatever our application was.
Okay. So let's go with that definition because I like it. What you got to understand, and this is hard for some people to get. I don't know why, but everything has a bandwidth. Every electrical thing has a piece of wire. You know the wire you hook to your cable TV? You can't put whatever frequency. It only works for a certain range of frequencies. The frequency can be too high or too low. It won't work the way it's designed to work. That cable actually has a bandwidth. A speaker has a bandwidth. Any electrical thing, especially if you're sending information back and forth, has bandwidth. So your ears have bandwidth. What's the bandwidth for human hearing? What is the bandwidth? How low can we hear? That's a perfect example. How low can we hear? Well, the lowest we can hear, it's going to vary from person to person, but on average, the lowest we can hear is 20 hertz. Anything lower than that, now if you look it up, some people might say 15, some people might say 20. Let's go with 20. The lowest we can hear is 20 hertz. Anything lower than that, you don't hear it, you feel it. It feels like a vibration. What's the highest our ear can hear? What's the highest we can hear? Anybody remember?
Was it 200?
21,000 hertz. If the lowest you can hear is 20 hertz and the highest you can hear is 21,000 hertz, that means the bandwidth of your ears is right here. Your ears, even though they're biological organisms or whatever you want to call them, have a bandwidth. I failed biology, guys. What is this thing you use to talk with your larynx, or I don't know what it is. Your vocal cords, I guess, has a bandwidth. People can sing real low like this. They can sing real high like that, but there's a range. There's a low and a high, probably way lower. You can't get much higher than that. I think the highest for human voice is about 3,000 hertz. And if you shut up, if you're not saying anything, we can say it starts at 0 hertz. So here's the bandwidth for voice, for your voice box or whatever the name of it is. I'm not a biologist, I don't know, but you know what I'm talking about. So everything has a bandwidth. Well, if we go with Jacob's definition of bandwidth, does that mean that frequencies above 21,000 and below 20 hertz don't exist? Well, you know that's wrong. We know there's frequencies above it. What does a dog whistle do? When you blow the dog whistle, it sounds like air going through a tube, but dogs and cats and bats and other animals who God gave a bandwidth greater than ours, they can hear up here somewhere. So it's not that the signals don't exist, it's that your ears can't respond to anything faster than that. They can't move faster than 21,000 cycles per second. So what happens is those signals are attenuated. Your ears up to that frequency, when you go past 21,000, it starts to attenuate like that. So here's a problem. Here's a practical problem. If I want to reproduce sound, so I record sound, that's sound right here. Here's the bandwidth for sound, basically, that we can pick up with our ears. It turns out it's impossible to have one speaker produce in an efficient way this whole bandwidth. Think about this. From 20 all the way up to 21,000, that's a big spread. So it's impossible for manufacturers to produce a speaker that has a bandwidth that wide. So what do? Well, what you do is you break it up. I might not be able to make a speaker to respond correctly to frequencies from 20 hertz up to 21,000, but I might be able to do this. I might be able to break it up. And maybe this one right here, maybe right here, this is, I don't know, maybe it's 1,000 hertz. And maybe this one right here, I don't know, maybe it's 15,000 hertz. So if I'm smart about it, if I'm going to make a speaker, you see what I can do? I can't design one speaker that will respond equally well from this low end to this high end, but maybe I can break up this bandwidth, I can break up this frequency spectrum into smaller pieces. Maybe I can make a speaker to respond well for this piece, and this piece, and this piece, if I can't make it respond well for the whole thing. And let's call these frequencies right here our low frequencies. Let's call this right here our high frequencies. And let's call this right here our middle frequencies or our mid-range. And so I got to have not one speaker, but maybe I can have 3 speakers that together can give me this whole bandwidth and reproduce the sound that I want with high fidelity. And so maybe I design a speaker to respond to the low frequencies. So the low frequency is going to move real slow. It's got to move and push a lot of air, so it's going to be really big. Let's call that a subwoofer, or sub for short. And this high end over here, the speaker's got to move really, really fast, so it can't be really massive. It's got to be small. So it's got to be able to move back and forth real quick. Can't have a lot of mass. Let's call this our tweeter. And in between the sub and the tweeter, we'll call this our mid-range. So now just looking at, basically we started with bandwidth. Just looking at bandwidth and understanding a little bit of acoustical physics, we can figure out that, well, maybe I can't get one speaker to respond equally well to the whole bandwidth for our ears, but I can break this up and get maybe 3 speakers to respond well enough to produce whatever I want with high fidelity. Well, the question is, okay, what would this look like? What would the circuit look like? Well, this is where I'm saying we start with the problem from just a statement. Now let's work with those graphs. What would those graphs have to do? What would they have to look like? Well, okay. probably what I want, is there a filter that will allow, see, here's the problem, and you might have done this before. You take a subwoofer. Anybody ever done this? You take a subwoofer. That's the big speaker. And you hook just a subwoofer with no filter, no nothing. Just a subwoofer, you hook it up to the output of your radio or your whatever your device is, right? You hook that up. What does it sound like? And I'll give you a hint. It begins with it's a 4-letter word that begins with the S and ends with the T. What does it sound like if I hook a subwoofer straight to the output of my audio device? Or you get the same effect if I take a tweeter, because if you take a subwoofer and you hook it up right to your output of your audio device, here's what it's trying to do. It wants those low frequencies because they move real slow. It can respond to those, but mixed in with that, I have these high frequencies that it can't reproduce. It's trying to it's trying to reproduce the lows. It doesn't really know what to do with the high. It sounds like crap. The same is true of the high end. So what you got to do is separate out the frequencies and send to each speaker the frequency is designed to handle. Is there a way I can separate things out? Is there a way to filter out the frequencies? Yes. So what would that look like graphically? What would it look like? What would the response curve for this system using these numbers, what would that look like? And to make it easy, let's start this at 0. What would the response curve for this system look like? Tell me what to draw. What kind of filter would I need for the subwoofer?
Low pass.
I need a low pass. I need a LPF. I need a HPF. What would I use right here? What would I use?
Called a band pass.
Exactly. You see what I'm saying? So we don't even doing this kind of design. You don't even start with a circuit. We start with a problem statement. We started with some physics. We started with just understanding the problem. From that, we made this diagram, and from that, now we're naming filters, and now we're going to look at the graphs. But we all know what this looks like. What does an LPF look like? Let's draw it. I want to hook up a filter to my sub so that it lets in the low frequencies and attenuates the high frequencies because I don't want it to try to reproduce those highs. So I got to hook up a filter. Filter separate. Here's what I want to separate out the lows and get rid of the highs. So what I need is LPF, and the response for that is going to look like this. Right? Now, this 1,000 hertz right here, see what's happening? It's like I'm going from one band or one filter to another filter. I don't want a gap there. That would make the music sound crappy. What I really want, where one speaker kind of falls off, that's where I want the other speaker to pick up. So you've already told me I need a BPF for that mid-range speaker. So if I look at the BPF response, I know what it looks like. It looks like that all day long. But I got to design it in the way to where this point right here is the critical frequency for both filters. So I want my passband response to look like this. And I got the same problem when I get over here to the tweeters. I want the other end of my passband filter, as it starts to attenuate, I want this other speaker to kick in and start to pick up where it starts to fall off. Right at the 50, this should be kilohertz. This is kilohertz. Right? So I know my high pass response looks like this. But I got to put the critical frequency in the right way. I want it to look like this. You see it? So that if I design it correctly, my critical frequency, that point right there, gives me my FC1. And this point right here gives me my FC2. You see it? And look at this. So my subs, look at the passband for my subs. The passband for my subs is right here. This is my passband. This is for the subs. This is my passband. Any of the high frequencies won't go to my subs. It only has to reproduce that which is designed to accept. And look at my tweeters. Look at that. Look at the passband for my tweeters. And the mid-range speaker doesn't want real low, doesn't want real, it wants something in between. Look at the passband for that. It's beautiful. Here's my mids. You see it? Now, if you're in the audio, I know I usually have a whole room of people full of audio, but over the years, they seem to have died off because, I don't know, back in the day, you could hook up your own audio system in your car or your house, component set, and people were really into audio. But now, everything is just, in your car, you can't change out the radio anymore and hook up your own stuff. Most people are into this like they used to be years ago. But if you were into this, you probably heard of the term crossover point. Crossover point. Some amplifiers actually have a little switch where you can adjust the crossover point. I don't know if anybody ever heard of that, but if you're in the audio and amplifiers and you've heard of the term crossover point, you probably didn't know what it meant. What I'm about to show you. You see these points right here? The 1,000, and those are arbitrary points that we pick. We didn't have to pick 1,000. I could have picked 1,500, right? But once you pick it and design the system around it, now look at our graph. You see how my low pass and then my band pass kind of pick up right here and they cross over each other at FC1. FC1 is a crossover point. And on the other end of this, from my middle and my tweeter, FC2 is a crossover point. So when you adjust your crossover point on your amplifier or your equalizer, whatever, you're actually adjusting a filter. All an equalizer is a filter. And you can adjust the crossover points to satisfy what, audio is a personal thing. But you can adjust these points to whatever sounds good for you. But you can see why they termed it crossover point, because it's where these graphs cross over each other to go from one pass band to the next, which feeds the proper speaker. So now the next step to this, if we were actually doing this, would be, okay, well, let me design the box for the LPF that will give me the correct FC1 to give me that response. And let me design the box for the pass band and the high pass filter to give me this response. And I would design it, I build it, I hook it up, and then it will work. And then they have to pay you a lot of money because this is something that everybody can't do. But my point is this, guys. We started at a really, really high level, and we just understood some concepts about filter action and, to get a fix on how this works. But I don't have time now. We'll do some calculations next time. So hopefully, I actually meant to do some calculations today, but I got kind of carried away with this stuff. You can easily get carried away with it. But if you really look at this, it explains so much. And these filters, looking back, years ago, I had a business called Cincinnati Car Alarm. And it was an automotive electrical business. And me and my partner started when we were in college. We would repair electrical systems. We would hook up alarm systems was our main thing. We would also hook up stereos and amplifiers in cars and just do different electrical work to cars. And I remember it was a store called Radio Shack. They're not around anymore, but Radio Shack was a store where it was an electrical hobbyist dream. You can go buy resistors, capacitors. They had all kind of stuff that were kind of techie stuff. And I remember when we had our business, sometimes you hook up, depending on the car, you would hook up, say, a stereo in the car. And when you start the car, you hear a whine. It's called alternator whine or generator whine. You hear a high frequency whine when you hit the accelerator. So if you're sitting there with the car in park with the engine running, you hear like a zzz in the speaker. And when you hit the accelerator, the pitch of it will increase. It was called alternator whine. What you would do though, to fix it is you go to Radio Shack and you would buy basically it was a capacitor and inductor. And you would put it on the line of the radio, the power line of the radio, and it would remove that alternator noise. And you wouldn't hear that whine coming out of the speaker. Well, I didn't know what it was then, but now, once I went through my studies, I know it was just a filter. I don't know, it probably was a notch filter to take out that particular frequency of noise so that it didn't kind of propagate through the system and come out the speaker. So these filters are really, really something that you can wrap your mind around, and they're very, very useful. It doesn't just work with audio, it works with any kind of electrical system. I can do the same thing with light. Light is, well, a light filter is a little different, but the concepts are still the same. So I think I talked myself into not getting into an analysis problem today, but tell you what I'm going to do. I'll put the topic sheet up, and then I actually have a problem where we go through and do some analysis, and there's some other terms that I want to talk about. So one of the things I want to talk about is gain. Remember earlier I told you that gain is something I want to talk about. I'll explain that. But I got about a few more minutes. Let me talk about one more thing, and then we'll end this session. I want to talk about one more thing. Remember I told you you can use a transformer as a filter? I want to talk about that, and then we'll end the session. So that'll just take me a minute. But before I get into that, because I went through a lot here, is there anything that I need to talk about? Any questions over what we talked about so far? We didn't do any analysis. This is all conceptual stuff. I didn't mean to spend much time on the concepts, but hopefully it was worth it and you guys learned something from it. Now we got to get down and dirty with the numbers and do some calculations. So we'll do that next class. But is there any comments or question on what we have talked about so far? Any questions? Okay, well, if there are no questions, let me do one more thing. This is quick. I want to show you how you can use remember I said you can use a transformer as a filter? So let me show you that real quick, and then we'll be done. So and we'll come back to this. So if you think of a question, you can ask me on next class. And so it looks like I'll get the filters, and the topics I have not talked about is superposition, Thevenin, and three-phase power. So, and we're going to do lab that last week. So I don't know how far we're going to get, but I may take up Jacob's suggestion and just video some of that anyway. You guys can watch it at your leisure. Of course, I wouldn't quiz you over anything that I haven't lectured over. You have a chance to ask questions, but you might be interested in some of that stuff. So we'll see how it works out. But let me actually I'll show you the transformer, and I can show you some other stuff next time. But anyway, there is let me talk about something called DC insertion. Now my spelling is terrible. I think that's insertion. I think that's how I don't think there's an S there. DC insertion. I should never try to put it on the board without first looking it up. But let me show you what it is. DC insertion is this. Let's say I have an AC source. 2 volts peak to peak. Right? If I made a graph of that, here's what it would look like. Right? Where this peak value right here, if it's 2 volt peak to peak, then that right there is 1 volt peak. Now what I do is I'm going to add a battery to this. $10 volts. If I add a 10 volt DC battery to this circuit that has a 2 volt peak AC source, what do you think is going to happen to that graph? Anybody? What do you think is going to happen? What's going to happen is the AC, if I can look at it, and you can actually look at this on the oscilloscope. This is what the oscilloscope does. It lets you see it. If you add this to the circuit, what's going to happen is, if this is my 10 volt signal, my DC, then the AC is going to jump up here like this. And so now, where the peak value was 1 volt peak, it's still 1 volt peak over here, but now my maximum voltage here is going to be 11 volts. And my minimum voltage here is going to be 9 volts. You see that? So this is what I mean by, I don't know how you spell insertion. I don't think that's right. But this is what I mean by DC.
It's got an S.
Change this to an S? Like that?
I think so.
Okay, that looks better. But you see what I'm saying, right? If I insert DC into the circuit, it raises the AC up to a DC level, and then the AC rides on top of the DC. Okay, so why am I showing you this? That's probably what you're thinking. Well, it turns out that certain devices, you put in AC and DC, and on the inside of the device, they get mixed up together. But you might want to, what comes out, you might only want AC or you might only want DC on the output. Often what you want to do is remove the DC and only let the AC come out. Now, one example of that I've already talked about. One example of that is an amplifier. Let's just talk about a basic amplifier. So if you think about a basic amplifier, it actually has 2 inputs. If you ever hook up an amplifier in your car or your house, there's 2 inputs. First of all, there's a power input. So you're going to have a red and a black wire. Let's say this is an amplifier for your car. You're going to have a red wire, which you hook to the positive terminal of the battery, and you're going to have a black wire, you hook to the negative terminal of the battery. That's your one input. That's your power input. And then your third input, you got a radio or a CD player. You got some kind of audio. Oh, you can't see over there, can you? You got some kind of audio device. So it might be your cell phone, it might be a radio, it might be a CD player, some kind. Well, what is audio? Audio is just complicated AC signals. It's AC. And you're going to also put that into the amplifier. So if you were to look inside of here, when I say look, I mean using equipment like an oscilloscope and meter, you will see inside of the amplifier, you actually mix the AC and DC up together. The problem with doing that is, on the other end of the amplifier is a speaker. And a speaker is a current-driven device. What I mean is, it takes current, not voltage. It's driven by current. It works by current. Because it's an electromagnetic device, and you know, the magnetic field is proportional to current flow. Not voltage, but current. Current makes magnetism, which makes the speaker work. And so it's a current-driven device, and the current that moves it back and forth is the AC current, not the DC. So when you hook up the speaker to your amplifier, you don't want DC in your speaker. That's not a good thing. You only want AC making the cone move back and forth. So the question is, okay, well, how, if I got it all mixed up inside of here, DC insertion, how do I separate the AC from the DC? How do I filter it? Now, we could use one of the filters that we talked about, but consider this. What if I have a transformer? What if I have a transformer hooked up to a 10-volt battery, and I put my voltmeter over here, or my scope? I hook up over here. What would I see on the secondary? What would I see on the secondary, and why? How much voltage would my meter or my oscilloscope read? What would I read?
I don't think you'd see any, would you?
You wouldn't see anything.
DC
Why not?
DC can't jump the gap.
Why not?
Because the inductor doesn't work with DC, right? Because for the yeah, you need the motion of the alternating current going through the coil to make the magnetic field, right?
Yes, you guys see it? See, this is what I like about this class. When I told you I teach from first principles, I don't just come in here and start throwing these rules at you, and it's not based on anything. If you learn from Faraday's law is a first principle. And just by understanding Faraday's law, Faraday says you got to have a coil. But we got that. We got two of them. You got to have a magnetic field. Well, if I have a voltage source hooked to a closed circuit, there's current flowing. If there's current flowing, it's going to produce a magnetic field like that. But as Jacob said, what I don't have is motion. Faraday says you got to have motion. And the way we got the transformer to work is I put an AC signal here. The varying current caused the magnetic field to vary, which gave us the motion to induce voltage over here. So remember that circuit I had? I had an AC source, and I had a battery that was 10 volts. And I called that DC insertion. If I hook up that same circuit right here, this is 2 volts peak to peak. Let's use superposition on this. The 10-volt source is going to make the magnetic field do this, but it won't move. It moves up, but it doesn't move. Only that 2 volts peak to peak moves the magnetic field enough to give me a little bit of variation to induce motion to give me a voltage on this second side. Now, if the turns ratio are equal, let's say that the primary turns and the secondary turns are equal to each other, then what I'll get over here is, even though I have this signal on the primary side, I have this on the secondary side, because as Jacob said, DC can't jump the gap. Well, DC, there's no motion in the DC to induce voltage on the secondary side from the battery. Only motion here is provided by the 2-volt AC source. So over here I have pure AC. I've used that transformer to undo the DC insertion. So what you can do in your amplifier, now this is done inside the amp, but let's say it wasn't. All you got to do, if you don't want DC in your speaker, you take a transformer, hook that to your speaker, and you're good to go. You only have AC in the secondary side of that transformer. You've undone the DC insertion. You filtered out the DC using the transformer. Whew, that's a lot. Now you can do the same thing with a capacitor, but we'll have to talk about that next time because I'm tired, I'm hungry, I'm thirsty. So we gotta do it later on. Plus I gotta use the restroom, I gotta pee. I've been holding it for like an hour and a half, but I gotta go. So anybody have any questions, comments, whatever?
Sorry, I missed, if the turns ratio was equal there, it would be 2 volts on the other side?
Yeah, it doesn't have to be equal.
I'm curious, you only use the AC for the math? Only the AC component?
Yeah, well, the reason we're only using the AC, I'm gonna look at the reason we're only using the AC component is
It's the only part that's moving.
what's driving with this is a speaker, and you don't want DC going through a speaker. It's going to cause power to be dissipated in the coil that you don't want. Only the AC component of the DC insertion do you want in the speaker. So how you take out the AC? You can do this if you want. Put the speaker on the secondary side of the transformer, and the DC never goes into your speaker. And the only reason the turns ratio don't have to be the same.
No.
But I was just pointing out for math purposes that if I wanted that 2-volt signal without the DC, make the turns ratio the same, and I have this graph over here and this graph on the primary.
Okay, I guess I'm just trying to figure out the math for like if you wanted to solve power or current.
Oh, no, that's another problem. I'm not.
Oh, okay. Sorry.
Yeah, I'm not. No, that's good. I like for you to think like that, but I'm just saying, we're not getting into any of the engineering and design. That's not what my purpose is here. All I want to do today is to show you conceptually how these things work. You know, understanding the concepts and the physics, that's one thing. But when you actually design and build this stuff, the engineering is where that's the tough stuff to get this stuff to work. So yeah, we can dig into the math and we got to figure out how you can do that, but that's not the purpose of this. Usually when you teach, you want to start at a high level concept because you can easily get lost in the details of the math. So my objective, and I hope I was successful. My objective was to help you to understand how you can use a resistor, capacitor, inductor as a filter to separate frequencies, and to show you why you might want to do that. Now, we didn't actually design the circuit. That's another class. But you can see from the concepts that it's possible, and actually the learning curve to actually doing it is not that big of a. Now you can probably go to YouTube and dig into this a little bit more. You can actually do the math on too. In the next class, we are going to do some math, but we're doing an analysis. We're not doing any design. So we're going to, given a certain filter, I can calculate my critical frequency. I can calculate my pass band. I can calculate my amplitude. I can calculate a whole lot. That's the stuff we're going to get into. Designing the filter, though, that's a whole other topic there. That's beyond the scope of this course. But to me, if you can understand how it works, it makes understanding how to design a system like that a little bit easier. So sorry, I can't answer that off the top of my head, but let's see what the next class brings. So guys, I think that's it. I'm all pooped out right now. I'm tired. So hopefully this gives you something to think about. If you want to read the book on filters, you can. I don't care. Or look at YouTube. I'm only going to test you off of what I put on the board and in the notes. But if you want to read it to get a more full understanding of it, you can do that. But make sure you understand what I've talked about. Rewatch the video if you have to. And other than that, that's all I have. So if you guys don't have any questions, have a great rest of the day. I will see you on Wednesday for our final lecture. And then Monday of next week and Wednesday of next we'll meet at the school and we're going to do labs. And I may give you a lab before then that you can do kind of quick and dirty lab at home. I'll see. So guys, have a great rest of the day, and I will talk to you soon.